Yeah, good afternoon to you all. Let's continue our discussion with the applications of convolution neural networks to computer vision. As we discussed before, computer vision deals with inferring from images or videos. So, processing is not just enough, we would like to infer, means we would like to know how many persons are there, where the persons are, or what's happening in that scene. Let it be with persons or without persons. So, what's the whatever is the inference we would like to do from images or from videos, how do we do it? So, in some the primary task of inference is classification, one of the primary tasks of inference. Say where we want to, based on the images, we would like to classify, is it a cat image, dog image, person image, or so and so person image, is he the same person that we would like to detect or find. What is the probably classification also can deal with different kind of say digit recognition, iris recognition, biometrics and many other things. Of course, it has applications in many other domains, medical image classification, blood cells classification as we discussed, also cancerous, non-cancerous kind of classification of cells and in many other domains. But there are other important tasks in computer vision. This is referred to as semantic segmentation. Semantic segmentation means instead of labeling the whole image at once, can we label each pixel to one of the class? Say, can we say that this is belongs to background class? Can it belongs to a mountain class? Can we label each pixel of the cat to cat class and so on, grass class and so on. So, this is referred to as pixel segmentation, pixel based classification or semantic segmentation. Okay, so we want to give the semantics to the image or the scene that we have. So, this in this task, for example, how many number of labels or we would like to generate is equal to the number of pixels in that image. So, unlike where you want to give one label for a whole image, it is like we would like to give the dimension of image is 100 cross 100, we would like to give the labels or the output also of 100 cross 100 dimension. Okay. So, this is referred to as object detection, where on localization. Object detection essentially is to localize an object. So, we are not interested or not enough to say that there is some object here, where is that object is of interest. So, at what xy locations it starts and what is the height and width of the object. This is one typical way of localizing an object, height, width and xy. So, four values we have to get from the image that we show. If you want to localize a single object, if you want to localize multiple objects, then we need to get more x, y, h and w's for each object one kind of. There is other task called instance segmentation, where we are not interested in background as we do in semantic segmentation. We are interested in the foreground objects. Say if I am particular only about humans, I just find the instances of humans where they are and try to give the instance segmentation on humans. So, like that, and each instance is different from other instance. So, as each human is different from other human, I would like to perform a task differently for different instances of that scene. Also, that is done through instance segmentation. Of course, there is one more task called combining these two, background semantic segmentation and instance segmentation, referred to as panoptic segmentation. Sometimes I would like to give the single label for all background, but each instance I want to give different labels. Now, what we see is we try to see, we will see some of the architectures or development of the deep learning methods for performing these tasks. Of course, these tasks have been there since long, and computer vision has dealt long way in terms of developing methods for each of these tasks. But the deep learning from its introduction has shown tremendous improvement in terms of the performance to handle each of these tasks. So, assume that we now want to have a network based deep learning based solution or a convolution network based solution to classify, to make the instance segmentation of this image. What is the typical way of doing it? A very crude method if you want to do. Say each pixel I have to give one label, let it be a grass, cow, sky and so on. What should I do? I have a small network, assume that network I will put at every location and take a small patch and then give that patch to this network and try to label it, right. So how many times then I have to apply this network if I want to label each pixel here? If it is 100 cross 100, if this is 100 cross 100, how many times I have to send apply this network to make the labeling? 10,000 side, 100 cross 100, 10,000 times I have to apply. And in training also is like that. So it's not very effective way, because the whole image has the, say I am putting a network here exactly at the next pixel. So there is a commonness of information between these two pixels, and I am not using effectively. And also the whole image can be given at one stretch if possible, and get the labels at one stretch. Why to run it this for 10,000 times? Okay, so the developments headed towards that, and this is one development where we give the image and try to get the labels for all of them. The remarkable ability of this deep learning is that as we don't essentially fix the filters or extract the features handcrafted, we can learn the filters or the feature extraction stage also and perform the classification also, driven by the objective function or the cost function we have. So if we develop the final cost function in such a way that we get the labels for each of the locations, then it is good enough to train this network. So how this is referred to as a semantic segmentation network. A kind of one example of this is Signet. What they does is, we have 100 cross 100 image. We have at each location we provide the ground truth label. So we have 100 cross 100 labels, 100 cross 100 predictions of the network. We see the error in this 100 cross 100 image label image, 200 label values to predict the actual values. These 100 cross, at each location we have an error value, right? We group together and then back propagate. So the back propagation is done as we discussed in the morning. Wherever which are dependent to this pixel output, they will be updated according, they will get the update from that error. So it's the this is one possible provision to get the learning of a network to give directly pixels for all, labels for all pixels. But the problem, there is one problem with this network. What do you think is that? The problem with this network is, see, this is 100 cross 100. This is a filters are also 100 cross 100. Okay, and then if I want 10 filters, okay, each of the filter has to be applied at each pixel, is it not? The computational complexity all through is 100 cross 100 into those many filters or dimension of the filters. So it's very high. So then the just after this, the immediate developments are to see if can we reduce the dimensionality, the complexity, and still get the labels at the image dimensions. So what the idea is to use the structure like we have in CNNs to extract the features up to some level with the convolutions and downsamplings or subsamplings or poolings. Then what we have in this process, we have the compact representation of the information and extracted or encoded the information very well up to here, and we have actually lightweight network to do that, or relatively lighter weight network to do that. After encoding, what we need to do, the encoded information is directly useful for classification but not for pixel level segmentation. So we have to bring back to the original image dimension to get the labels at each pixels. So that's done through a decoder network. Just exact replica of this is usually used here. In terms of the architecture, in terms of training, there are also some commonness that will leverage from here to here. But these two can also be independently, in sense that it can be trained in the way that upsampling to downsampling is done here. So in training, downsampling to upsampling will happen for the gradients. Whereas here, it is upsampling to downsampling to upsampling is happening here. So while training with the errors, we downsample the errors. So same thing happens. So there are different ways in which they upsample, because upsampling is not very, it's a ill-posed problem. So upsample by just replicating, upsample by putting zeros, or upsampling by max pooling. If I do max pooling, for example, I take this 5 from here. Okay, while I use the other, this is while downsampling. While upsampling, what I do, I will put this error, whatever I have, at this location. Okay, I will put the remaining locations 0, because there is no propagation in the forward direction. So some tricks like that are used while bringing the encoded information to the decoder, and then it is trained accordingly. So the model that uses this is referred to as Signet, that has demonstrated good accuracies in terms of pixel level classification or segmentation, instance segmentation. there are other ways in which we can upsample. There are methods to train the filters itself to upsample. So like we are doing convolution from one convolution layer to other convolution. If we do with a stride of 2, for example, what's happening? Stride means we shift by 1 pixel and do convolution there. So the dimension will be half, because we are shifting one pixel and doing convolution. Similarly, while doing upsampling also can done through a filters, the learnable filters. What do? Is they put the filter here, or bigger size filter here, exactly put at the next location, they tile them. So in this way they can upsample as well through learnable filters. So this is referred to as transpose convolution. The name transpose convolution comes because those who know convolution writing in matrix form can write it like this. Okay, those especially some kind of books specifically write or deal the convolution through matrix operation. That can be written in a with a transpose operation here. So that is that's why it is referred to as transpose convolution. Here we learn the filter. Say if we are learning this filter, in convolution we will be learning the other filter in the transpose convolution. So there are follow-up works on instance segmentation. The kind of works that are try to leverage from the computer vision community. See, if you want to extract good features for it, what we usually do is we see the signal or the image at multiple resolutions. At different resolutions, some of the different objects which gets highlighted or can be we can effectively extract their features. So there are some methods that use the multi-resolution kind of framework in the deep learning. What they try to do is they extract the features, say they sample the either image and extract features at different resolutions of the image, or they sample the features extracted and try to infer from one resolution of the features to another resolution. So this is conventionally used in computer vision, and these similar ideas are borrowed even in used even in the deep learning frameworks. The idea is at this resolution bigger objects may look compact and fine. At this resolution even smaller objects may have their features retained. So and while combining we effectively will have a effective procedure to blend them. And these usually give better accuracies in terms of the either segmentation or any other tasks as well, and these are recently also seen to be robust to some kind of attacks. That means if slightly perturb the neural network, will its results change drastically. So to such attacks as well, these are more robust. So this semantic segmentation is very well applied or demonstrated for cityscape scenarios. The one of the very important problem that many of the industries and researchers want to deal is on the segmentation of the cityscape or the street scenarios, where we would like to identify the cars, persons and so on very accurately. And this is useful for self-driving cars development and so on. This can also be applied in different fields. This is one application where it's shown to segment the roads and buildings. This is on some other natural scenes. This is brief about the segmentation methods. Now let's move on to discuss on the object detection methods. Conventional way of detecting object. Say if I want to detect a cat or a dog or a person. Okay, what is usual way? If we don't know anything about say deep learning or even image processing, if somebody asks us to detect an object, a person here, what do? As we discussed in the previous discussion, if we want to detect face, for example, we try to see the template for face roughly and try to see if we can match it, and then wherever the correlation gets higher, that's the region where we say that the face is there. Or we try to get effective filters that imitate the face and then try to run across and see the correlation where it is higher. So the usual procedure or crude procedure is to, if I want an object, let's get a template of it and then try to match, and wherever the object detects is detected. But that approach is very costly. So we will see now what are the developments that we had in this direction. One thing to note is in terms of object detection, there are for each of these tasks there are good data sets, especially driven by the requirement of deep learning. As we discussed in the morning discussion, To train the networks, each of these networks, we need large data samples, large samples. So there are data sets for object classification. There is in fact 1.5 million images with 1000 classes is usually referred to as ImageNet data, that is widely used for assessing the object classification frameworks. For object detection, we have we again have plenty of data sets now. And if we see in our large scale, the accuracies till 2012 are only up to 40% mean average precision, with which we see precisely locate the object and across several classes, and that is boosted up very well by the deep learning methods. The ability that deep learning methods has in terms of object detection compared to the conventional methods is much higher, as we can see now in the attributed to the better ability of learning the localizing the objects and localizing the features of the object. There are several developments in this direction. So COCO and Pascal VOC are the well-known data sets, and mean average precision is the metric, and there are several benchmark methods. One advantage or the disadvantage with the deep learning is most of the methods that are developed, architectures that are developed are available for direct use and implement application on different domains, and these are all the well-known well-known models that have celebrated models which have shown good improvement in terms of object detection, and some of them both for object detection and segmentation. I will discuss a couple of intuitive ideas that has emerged in developing these models. So one way of doing, say, if I want to detect multiple a single object for time being, if you want to localize this object, what is important is we need to know what object it is and what where the object is. So usually if I want to know which is the object, we perform classification. If you want to know where the object is, we will perform we need to find out x, y, h, w of it. So we perform regression. So what we need to do is we once we extract the features through the deep neural network, we use these features to identify the location of the object through regression on x, y, h, w values and classification of the label of the object. So this is performed together with the same features, and the cost function is a combination of both of them. But the problem is when we have multiple objects, we cannot simply go with a classification and regression framework. We may have several objects, and one way of dealing with it is let's try to get each of the object annotated by different x, y, h, w's, and try to run a deep learning model to get the localization and the class label for each of them. But running them for several for each object independently is, as we discussed in segmentation, is not a good approach. What usually is done is, so we would like to first identify the probable regions of the object, and then from the probable regions of the object we would like to say what object it is. So it goes usually in a two-stage manner. Most of the initial developments are with these two-stage object detectors. What they do is initially, so they scan each region. Usually in computer vision there is a method called selective search. What they want to do is they take all possible regions, and in which of the regions there is a possibility of object. Say usually what the procedure is to knock out the regions where there is no object. Can you tell actually any region if I want to knock out, if there is no saying that there is no object, what may be the criteria? If I just want to knock out that this region there is no object, what do you think is the criteria? In that region, no edges, okay. What still better a quantitative measure? No variance at all. If I see the pixel variance, it will be close to 0. So there are some methods like that to identify the region of object, whether in that region, given region, object is there or not there. Once we identify them, then we would like to say whether what object it is. While identifying the region of object, since we take several bounding boxes, we also initially get the x, y, h, w roughly where the object is there, and in that region whether object is there or not. So that is done through selective search, and then subsequently we try to see what object it is. So the algorithmic developments, a combination of were initially combination of computer vision and deep learning. What the initial developments are to see each of the regions and see the object regions, and then get the features for them, and then try to use in the like for based on these features what is the exact bounding box and what class does it belongs to. But the problem is for identifying the region of object through computer vision, we need to do an XHAS2 search, and here for each region different networks are used. So there is a high computational complexity in getting the features independently for each region. Then the next development is why anyway we need the features for all the whole image space. So why don't we get the feature extraction, or why don't we get the deep features for the whole image at once, and then scan each of the region to see whether there is what object it is. So that's the first extract the features, and then from the features apply a select to search kind of thing to identify the object is there or not, and then further we try to identify which object it is. The next level of development has happened in terms of, see, initially even here the object regions are done through computer vision, and then for the regions are identified, we take the features and apply through deep learning what the class label is. The subsequent developments are, why to have a computer vision method at all, even to give the object region, why don't we directly use feature space itself to localize the object locations roughly XYHW and whether there is an object or not through a training like this. Here there is one you can consider an object detection network. What this does is, it doesn't tell what object it is. It just tries to tell whether there is an object or not an object. The primary task here is to know object or not object through deep learning, and then it's roughly localize the object as well. That is the first task. Given that task, again use another deep network. Of course, it's a follow-up network. Both are trained in an end-to-end manner. That means we take the loss function here, and that is used also to train this. Of course, there is another loss function separately for this. So what we want to do here is what class it is, and we also would like to get the label of it. So that is the next level. Both are done in a training together to identify the localization of object, or whether there is an object or not, as a primary task, and then what object it is, and better localize the object location. So this is a very celebrated method, in fact, for object detection, referred to as faster RCNN. This has shown good improvement with respect to the time of execution in terms of training and testing compared to the earlier developments. The loss functions are roughly based on the matching the pixels, maxing the XYHWs with respect to the ground truth through regression, and then classification scores through cross entropy. There is one more trick that, one more thing that people usually are interested or make use of is, as we discussed, analyzing the information at different resolutions. As I discussed in the previous discussion, one way of identifying is looking the object, we sample the image at different resolutions. So if we have 100 cross and 100 image, we see at say 50 cross 50, 25 cross 25, and then try to see the objects. That is one, we are sampling at the image space and try to look for different size objects or scale objects at different resolutions. The other way of doing it is, say instead of sampling the image, or instead of looking the image at multiple resolutions, can I look the filters, can I design filters that look at multiple resolutions? So we bring it, if we see with a 5 cross 5 filter versus a 15 cross 15 filter, the region I see is different, or the way we see the information is different. That is taken care as other way of addressing the multi-resolution or different scale, identifying the objects at different scale. But the idea that's used in fast RCNN is even better. The key contribution for them is to use the anchors. The processing is done at once for all the whole image and get the features in a given region of interest. Sometimes this region may be smaller based on the object, sometimes it may be bigger. What we do is we analyze these features itself through different anchor boxes. That is, after we finally get the features, we try to see at different lengths with small scale or different aspect ratios. So that's what is done. This is identifying the objects through the anchor boxes. When we do that, what will happen is, at every previously as we discussed, if we want to identify whether there is an object, what object it is, and then find the XYHW of the object, essentially XYHW and the class label are to be identified. Now in addition to that, at different scales given by the guided by the anchor boxes are also to be identified. So the computational complexity finally here increases by k times as number of different aspect ratios or lengths we see. However, it helps us to identify the objects at different scales. So it's well applied on different data sets, and we can see very good accuracies in terms of detecting the objects at different scenarios. Of course, there are associated difficulties or challenges still for these methods. This is another framework which is very celebrated and widely used again. This is referred to as mask RCNN. The ability of this mask RCNN is, in addition to detecting or localizing the object or different objects, it also can give the segmentation of the object. So it's not just detecting the objects. After detecting the objects, till the final stage roughly same as the fast RCNN. Here we try to give for the region of the object, region of interest of the object, we try to give a 2D mask where the based on the location of the object, and use this for identifying or giving the pixel wise classification as well for the object region. So this in a sense integrates the previous segmentation method or instance segmentation methods into the object detection frameworks, and once we detect, it does automatically the segmentation as well of the object region. So this is in fact even more celebrated or widely used than fast RCNN, and it is used not only for segmentation, this is also used for several other tasks. For example, this is pose identification. So whether a person is moving his hands or running, jogging, or what is he doing, or the expression analysis, all those things can be done effectively. The reason is actually this has the ability to segment, and we exactly can locate each of the part of the person or an object, and then we can say what where is it now. So XYSW will be there, one for leg, this leg, one for this leg, one for. So we usually have landmark points or some key points of the person to track, and all those points we try to regress and then identify in a frame to frame manner, and that can be done conveniently by this mask RCNN. There are some other developments for object detection. Essentially, they try to do without doing a two-level detection. Can we do in a single level of detecting the object without initially saying that whether there is an object or not, and then going for what object it is? Can we directly say what object it is and whether there is an object or not together? So this is usually done through a method called YOLO, and there is class of methods of YOLO. These are usually lightweight than fast RCNN and so on, okay, and faster, much faster than fast RCNN and other two-stage methods, but slightly less accurate than the two-stage methods. Now there are several other versions of these methods as well, which are almost all accurate, as accurate as the other two-stage methods. I will introduce or give some little bit intuition on the other computer vision application, that is visual tracking. So the problem in visual tracking is, if we have a object, if we have a series of frames or a video of an object, moving object, if you would like to, if we locate an object at the first frame, can we locate it in all subsequent frames? If a car is moving, for example, I just locate it in the first somehow, either with manual annotation or automatically. Now I would like to know where the car is in all the next frames, next set of frames. Not just a single object, but there can be multiple objects. All persons may be moving, okay, in a in general scenario, and we would like to track each person and give unique ID to that person. So if he crosses over the other person, or if he crosses over any other vehicles and so on, he should get uniquely his ID, so that we can identify where he is, and we also can easily assess on the actions and other things. So this is also very important application of computer vision. So what people usually do is to perform a correlation. Correlation is a building block for all the most of the methods of computer vision, because we want to see the similarity of the first the target object with where is it in the frame. So what they do is they extract the features of the target object, they do extract the features of the search region, and then try to, instead of correlating the image space where to locate where the object is, they correlate or convolve or correlate in the feature space. Wherever the correlation is higher, there we have the better identification of the object, and that we do in each frame. And as I mentioned, there are good number of data sets even developed for tracking, visual object tracking, to evaluate them or to train them as well. So as I mentioned, the correlation is considered, and we would like to see the correlation value being higher, being matched with the actual value of the location of the target, and that based on that we try to see that the response map shows the peak or the high value exactly at the location of the object where it is. The response map is obtained by correlation. Once we have the peak of the response map that is supposed to give the actual location of the object, we match with the ground truth location of the object and try to backpropagate. So, usually many of these things are also associated with challenges. Those who especially want to work in this area or usually submit their methods for challenges and evaluations, and the visual object tracking challenge is one of them. So, many of our previous works were through in visual object tracking challenge. Many of the students have worked in this area before. So, the problem is to track the objects in very challenging scenarios in background clutter or say fast moving objects when they are occluded and so on. So, there are some contributions from our students to track in occlusion recently. I will very briefly touch upon or discuss the intuitive idea of generative adversarial networks. This we can consider as one of the breakthrough after convolution neural networks, and this has elegance of generating the samples as well. We will see the ability of this through small details. So, what the problem usually so far we are discussing is how to classify or how to detect or how to track and so on. So, this is more of an analysis task. That means we already have the image with us and we want to locate where it is, and we want to identify what's class or what is the action happening there. But this method, what the problem that is posed now is, see, I have several faces with me. Can I say if I consider each, say I have several random numbers that is thrown out, say 5, 6 and so on, I will give some 1,000 random numbers or many 10,000 and 1 lakh random numbers. If I give all these random numbers, the question is not to generate one more, the question is to generate one more random number as well, but more than that, can we get the underlying distribution? What is the distribution with which all these random numbers have come? Not just analyzing what the distribution these have come. Can I generate with that knowing that distribution or without knowing that distribution? Can I without explicitly knowing that distribution or with explicitly knowing that distribution? Can I generate samples of this sort? Okay, if a person says for 5 times, okay, or 1,000 times or 10,000 times, can a machine continue? This is the question. So, the answer so far before GANs is almost no. But with the generative adversarial networks, at least there is a good ability to synthesize the images, synthesize the different scenarios like we see in real nature. So, for example, if we have actually faces, several large data set of faces, of course for training you need the large data sets again, but using that these GANs can capture the distribution of the samples and generate more and more faces. Similarly, any of the different objects. This is usually there is a good literature behind to perform this kind of task. The one way, very crude way of doing it is modeling the distribution itself with some kind of a known distribution and then try to get the parameters of the distribution if I have some samples. I assume that if I throw 10,000 numbers, I say that they are Gaussian distributed. I will just try to find out what is the mean and variance of the Gaussian distribution. Of course, once I get that, I can generate more little. But the other kind of problems are, this is usually done through maximum likelihood approach and so on. And there are other kinds of approaches where they don't want to make a parameterized distribution. They want to develop without parameterizing the distribution, they want to find out the distribution. So, that is usually there are some methods like Pargin windows and so on, try to do that. But the scenario here is much more complex because the images themselves are of like 10 power 4 dimensions and 10 power 6 dimensions. So, the feature vectors are the samples, it is not just single numbers. So, this much dimensional feature vector is what is describing the image, and we would like to generate such in such higher dimension. So, the initial developments are with respect to the autoencoders. What they do is, say for example, if I give an image here, I will try to say that there is an encoding and decoding happens. Finally, I would like to get the image back. So, the advantage of this is, even if we get an image with noise here, I may fill that gap somehow and get the noise free image here. Even if I have an image with small missing region 7, if it is written with some missing like details in 7, still I will be able to get 7 here. So there are the kind of application of this. These are referred to as autoencoders, and then subsequently denoising autoencoders, which will denoise and give the noise free images, and filling the gaps in the images through association and so on. But these methods have a limited ability, because they need to train with the same class and then get the same class with a little bit of for the same sample, and they can't generate new sample all across. And the advantage that usually taken from these methods is to take the decoded features and then use for classification and so on. But as I mentioned, you need to have the sample. From that sample, only that sample can be made better, or you can't generate a new sample. What this GANs frameworks, the idea has come is, say the question is, if we give a random noise, can I generate the, can I see if I have a Gaussian distributed samples, I give some Gaussian distributed samples of 1000 or 10,000 samples, can I generate uniform distributed samples? We take the Gaussian distributed samples and then generate the uniform distributed samples. The answer is yes in conventional terms to some extent. Even the statistical methods guide us to transformation of the distributions. But however, through the learning they would like to, they targeted to do, and for learning this we need some clue. So assume that this generates some value here, or some some other sample from other distribution. In that case, there should be some guiding one that is referred to as discriminator. What this discriminator does is, say if I want to, my aim is to generate from Gaussian to uniform. So I keep generating several samples, but this discriminator also generates several samples and try to see, is that matching with the sample that is there in discriminator, or close sample that is there in discriminator. So what the idea is, if we bring in purely on from generating any noise to image, then we would like to see, if I want to generate cars for example, I have several cars, and then try to see the generator that can it generate a car. The first initial answer will be no, because it will anyway give a false generation, or it will not generate the image that we wish. So the discriminator initially makes in a critic way, saying that this is false, the generated value of generator has generated false sample. Then it tries to say that it tries to give an error, quantification of error, and that when we train together in some nice fashion, we can see that the discriminator critic will help the generator to improve. So how does they do? So they does usually in a game theoretic manner. What is essentially done is, the objective of the generator is to maximize the probability to generate correct sample, whereas the discriminator objective is to say that it is fake. That's where we start, and then when they get trained appropriately, the equilibrium happens, and then generator is able to generate the samples that the discriminator has as real samples, and discriminator says keeps quiet. So the it doesn't have, then we assume that it is trained, or it can generate samples. So how is it usually done is, say if we have a say here, please note that assume that we have we have some random sample x, and we would like to generate some the sample of other distribution, and we have a discriminator here which is trying to see whether this generated sample is it correct or not. So G is the whole representation of the network. That means if we have whatever the layers and so on, I assume that after passing through the sample that I have, input random noise I have through this G, what I get is G of x. Okay, this G of x may or may not match with respect to the real sample Z I have. Okay, so if we give here if we want to be in line with that notation, Z is here, and Z is the sample, G of Z is the output, and X is the real sample. Okay, so this discriminator has real sample and also has this input. Both of them are taken as input to this discriminator. Since discriminator can compare both of them, what it compares is D of G of Z. When I pass this input, what the discriminator gives output is D of G of Z. D, whatever what D is here is nothing but the, as you have seen in neural network, it's function of something W1 into X, function of W2 and so on, right. So, the whole thing I represent as D here. This function of whole network is D, this function of whole network is Z here. So, it tries to see D of G of Z, is it matching with the X, okay, D of X. So, the objective of the discriminator, if you want to see first, the objective of discriminator is to say that, okay, the I just assume that cross entropy loss computation is known or can be seen. So, it tries to maximize the probability that this is real sample, okay. So, D of X, if we maximize D of X, it means that if I maximize the probability of getting D of X, so we assume that actually this function D is also such a function that will bring the output in probabilities, okay. So, this D itself gives the probability of X being correct, okay. So, now what we are trying to do is the discriminator function is to maximize D of X, probability of X being real sample, plus what, the minimizing the probability that D of G of Z. That means it want to say that the generated sample is not correct. So, what it does, 1 minus of D of G of Z is maximized. So, what is happening here, the first term is maximizing the probability of real sample being correct, that probability of real sample. The second term is, what is it doing, the prediction of the G of Z is not correct, okay, 1 minus I have used, so it is not correct. So, the objective of this is being maximized with respect to the all parameters of D, okay, for the discriminator training, okay. So, while the generator function is what, generator does not care about discriminator, of course it uses the feedback from the discriminator. What it tries to does, it tries to maximize the probability of G of Z, D of G of Z. Okay, if I pass through, if my sample gets passed through discriminator, I would like to get the maximum value. That is the objective of the generator. Okay, putting together what we have here, here is directly we are using D of G of Z, here 1 minus of this. So, we minimize here with respect to generated parameters. So, this is what the objective function that GANs does with. What they are trying to do, generator purpose is to maximize its sample passing through D of discriminator, okay, probability, but the when we put in framework, 1 minus of D of G of Z is minimized by in generator, whereas the discriminator tries to maximize the real sample probability, but they minimize the sample that is obtained by the generator. So, this is done in a iterative manner, and then this one, there are several difficulties or several aspects that are to be taken care while training the GANs, because this is a min-max function. There are two networks which are not directly interacting. So, after taking care of reasonable aspects of training, one can see that GANs can produce reasonably very good accurate image synthesis or sample synthesis. So, the initial experiments are to generate the digits, and then subsequent experiments are to generate images, and then initially the results were not that great, but later with several advancements while to train them better, to take the loss functions in an effective way and so on, we can see that we can generate very good images. Of course, the ability of GANs not just ends with generating images, they also enhance the ability of computer vision methods that we will see with an example. Also, they can help to see that at the feature level, like the attribute level integration. So, picking the some aspects of one image and put on the other. So, automatic colorization, all those are the advancements or the offsprings of the GANs. So, for each of these methods there are model juice, where you have several models to experiment or to develop further with. So, I will conclude with this small example, where in computer vision we can see that this can be considered how GANs play a role. So, this can be considered as a generator, generating a higher resolution image from the lower resolution image. This can be used as a discriminator, where it sees the generated image with respect to the actual super resolution image and try to improve the generating framework. This framework, this is like a conventional CNN or convolutional neural network for super resolution. This to putting together with the discriminator is the GAN framework. So I will conclude with this. You can see plenty of references for deep learning and deep learning in computer vision. As I mentioned in the morning, Professor Fifi Lee team Stanford has video lectures on convolutional neural networks for visual recognition. There are plenty of other references there. Thank you.